to listen to Clayton give us a talk about micronutrient management. So take it away, Clayton.
Great. Thanks so much, Tim. And as I mentioned to other people, uh, as you were logging in, I am recording this. So if you miss anything, if your internet fails, if you have a friend or neighbor that wish they had heard it, you can pass on the link that Catherine's been sending or that Tim has in the chat box, and you can watch this uh, video recording later. If you do have questions, please ask them. I'm here to answer questions. There's not that many people logged in. If you do have questions afterwards, please feel free to give me a phone call at the number shown here at the bottom of your screen, or send me an email at clainj@montana.edu. And as Tim mentioned, you can send a chat to everyone if you're a little shyer. I don't want everyone to see it. Just send it to me and I will do my best not to say your name. I will just read the question. So just for me to get to know you a little bit better, especially in the area of micronutrients, I would like you to type a number into the chat box that corresponds best with what you're seeing here below. So type in a 1 if you don't think you've seen any micronutrient deficiencies on your land. 2 if you've suspected them but you haven't verified them. 3 if you've verified them with tissue testing. 4 if you verified them with some sort of fertilizer trial. 5 if you've done both. And if you're, say, a crop advisor, do what maybe you have seen on some of your clients' farms. And then 6 if none of those fit you at all. So I saw 3 go by. I verified through tissue testing. Some 2s, you've suspected them. 2, 5, and a couple 1s. So Kim is speaking for some of her producers in her county. So that's all useful. Anyone else that cares to type in a number that fits you, even if it's 1 or if it's other. Suspected, verified through tissue testing. Okay, great. Thank you. That gives me a little bit of a flavor where you all are coming from. So micronutrients, even though they're needed in smaller amounts than macronutrients, are still needed. A plant cannot grow without any iron, for example. So let's look at a pie chart of what is in plant material. 94% of plant material is carbon, hydrogen, and oxygen. Another roughly 5% is the macronutrients, so nitrogen, phosphorus, potassium, sulfur, calcium, and magnesium, represented by this blue slice of the pie. Only about 1%, and probably even a little less than 1%, is actually micronutrients. And these can range anywhere from about 0.05 parts per million, meaning 50 parts per billion. Hard to imagine that. A few people on the face of the earth is what we're talking about compared to 7 billion. And the biggest micronutrient is chloride. It can be somewhere between 0.05 and 0.5%. So that really falls in between the micronutrients and the macronutrients. The red italicized micronutrients here, boron, copper, iron, manganese, zinc, and chloride, have all been found to be deficient in one field or another in Montana, some more than others. Most not super common, but chloride, for example, can be fairly common, boron a little bit in alfalfa, and we're seeing more pockets of copper in northeast Montana. So a big challenge with micronutrients is that they're needed in very small amounts. So it's hard to get nutrients in small amounts to plant roots. It's fairly easy to apply a lot of prills of, say, potassium or nitrogen, and they eventually make it to the plant roots. But how do you deliver on the order of ounces per acre? To put this in perspective, what I'm going to show here is 3 different crops. Crops are going to be over on the left-hand side. The amount of potassium, K2O, that's removed by that crop, just for perspective. Potassium is a macronutrient, but to put things in perspective. So 3 tons per acre of alfalfa removes almost 160 pounds of potassium per acre. Only about 1 pound of iron is removed, 3/10 of a pound of zinc and manganese, and less than 1/10 of a pound of copper and boron. So very little. If we look at chickpea and wheat grain, the amount of potassium removed is substantially less. The amount of potassium removed is substantially less than alfalfa. The amount of iron, zinc, manganese, copper, and boron is also substantially less. So all of these are well less than a pound, most of them less than 1/10 of a pound. Why am I bothering spending time on micronutrients? The reason is that we are seeing more micronutrient deficiencies as time goes on. And the reason for that is that there's a finite amount of micronutrients in the soil, and very few of us are putting any micronutrients back down into the ground. So we think deficiencies will likely increase and are increasing because the yields and the amount that's being removed of these micronutrients from fields increases. No micronutrients are being added, except for maybe a little bit in phosphorus fertilizer. So phosphorus fertilizer is mined from the earth. There's always some trace levels of metals. And it's been found that this phosphorus fertilizer, for example, has a little bit of copper. You do the math, that's not enough to meet plant needs. More zinc, it will meet some of the plant needs, but still a fraction of what the plant needs. Micronutrient availability is limited by low soil organic matter. A lot of micronutrients are released from soil organic matter during the year. Also, most micronutrient availability is limited by our high pH that is common in most of Montana. This is a figure that shows a soil pH goes from 4 to 9. The relative effect on micronutrient availability is shown by the thickness of these lines. So a thick line indicates high availability, a narrow line indicates low availability. Most soils in Montana are in kind of the 7.5 to 8.3 range, even though I've talked and will talk about soil acidification where we have soils down here. This is still probably 80% of Montana soils are in this range, where iron and zinc availability is low, manganese availability is low, copper is not horrible, boron's okay, molybdenum might be a little on the low side. And chloride is not affected by pH. Also, micronutrient availability is limited by the weather. So cold and dry conditions or very wet conditions can decrease, especially early season micronutrient availability. So the question I had on that previous chart is the alfalfa use of potassium on irrigated. So that was a 3 ton per acre yield. So that could either be a very good dryland environment, or that could be kind of an average alfalfa grass yield. And so that was for kind of a wet, dry environment or a kind of a dry irrigated environment. But that's a pretty typical potassium removal for 3 ton per acre. So it doesn't matter whether that 3 ton was grown with irrigation water or with rainwater. That's about how much potassium will be removed. So this is a really important table, and I'll show you why. It's basically pointing out the mobility and solubility of the 6 micronutrients that have been found to be deficient at one point or another in Montana. So boron and chloride are both very mobile and very soluble. That means they're mainly going to be lost from a soil environment through leaching or harvest. On the other hand, the metal micronutrients, copper, iron, manganese, and zinc, are immobile and insoluble. They'll be removed largely by harvest and also binding to soil. They probably will not leach. So you might be saying, well, Who cares? Why is this important? Well, it really affects fertilizer placement. You can put chloride on the surface of the soil, it will dissolve and it will make it to your plant roots. Conversely, if you put copper, iron, manganese, or zinc on the surface of the soil, it will stay there. It will not make it down to your roots. So you really need to put those metals down near the seed in the root zone or foliar apply them, meaning spray them on the leaves so that some of that metal is taken up. Another issue with micronutrients, especially these metal micronutrients, is, and what must be very frustrating to farmers who have deficiencies of these and gardeners who have deficiencies of these, is that there's actually a fair amount of them in the soil in a total form. But plants can't access total form, meaning they can't access minerals or metals that are stuck too strongly on the soil surface. So what I'm showing here is how much metal micronutrients we have total in our soils in Montana. Copper might be somewhere around 30, iron 38,000, manganese 600, and zinc 50. But look how much less is actually plant available. 2 for copper, maybe 16 for iron, so only 0.1% of the iron is actually plant available. Quite a bit less is available for manganese than exists in the soil, and quite a bit less for zinc. This is a slide that shows the for each of those 6 micronutrients, it shows what's called the critical level. So the critical level is the value, the concentration of these micronutrients above which you probably won't see a response to fertilizers. Below that level, you have an increasing chance of seeing a response, meaning a benefit to yield. So boron, and this data is from AgVi's laboratories. Sometimes their critical levels don't agree exactly with MSU's, but they're generally fairly close. So what they tell us by having analyzed somewhere around 10,000 soil samples from Montana back in 2017 and sharing this summary data with us is that about 50% of Montana soils have boron levels less than 0.8 ppm. About 57% have chloride levels less than 30 pounds per acre, which is kind of our rough critical level for chloride in Montana. Relatively few have copper levels lower than critical, only 1.4 for iron, substantially more for manganese, and about 32% for zinc. The 2 nutrients that I have seen and heard other people see that have the highest chance for deficiencies in Montana are probably chloride and zinc, though increasing reports, again in northeast Montana, of pockets in fields of copper deficiencies with levels less than this 0.5 ppm. So the question might be, well, are the percent of soil chloride or zinc levels below our critical level, have they increased in the last 15 years or so in Montana? And the answer is yes. In this figure, I showed data going back to 1998 all the way to 2017, and I've plotted on the vertical axis the percent of those 10,000 soil samples that were below the critical level. So for chloride, we can see that since 1998, the percent of low chloride levels has increased from about 28% up to somewhere around 60%. The percent of samples that had too low of zinc back in 1998 was about 10%. That had increased to about 30% by 2017. And maybe we're reaching some sort of plateau, or maybe this is just weather related and it's continued to go up. So that brings us to soil testing for micronutrients. If you don't soil test, it's really hard to know whether you're deficient or not, and if you are deficient, whether you should fertilize or not. So I would suggest, so one downside with micronutrients is there's been far less soil fertility research done on micronutrients than for nitrogen, phosphorus, and potassium. And therefore, we don't exactly know what these critical levels are. Sometimes they were developed in other states or maybe in Canada. So I would always recommend using soil testing for micronutrients in combination with other tools. Keep in mind these tests aren't always highly accurate or precise or even consistent among labs. And although critical soil levels are published, they're not always well established. For example, in Montana, we've seen a dry pea response to iron and manganese when the soil test level was above the critical level. So that's in an area when we shouldn't see responses. We've also seen that alpha did not respond to boron on low boron soil. So that's again opposite of what we should expect. Correlations between soil tests and tissue test levels and fertilizer rate guidelines are therefore not very well established. Another issue with the micronutrients is really high variability. We have high variability with macronutrients, but micronutrients might even be higher variability. So this is an image of a field in Saskatchewan where the light colored areas had relatively low levels of copper. The gray had kind of moderate levels of copper, and the really dark areas had very high levels of copper. So probably the only places on this field where you'd expect to see a response are in some of these white areas. But we as crop advisors will say sample 6 to 8 soil cores within that field, mix them together, send them to a lab, and maybe get a number, say around 1.6, and think we don't have any deficient soils, when in fact there's pockets of deficient soils. Any questions on anything that I've covered so far? And I'll give you some time to type, recognizing that it takes a lot longer to type than it does to just ask a question. So, and just kind of reiterate that metal micronutrient deficiencies are increasing in Montana. We don't have great, guidelines yet, but I will be showing you in the next couple sets of slides that there has been a fair amount of research, at least done by our neighbors to our north in Canada, that give us some flavor for responses to micronutrients based on soil testing. Okay, no questions. So on to tissue analysis. I would recommend doing tissue analysis, especially if you suspect a deficiency. There's a tool we have online in what's called Nutrient Management Module number 9, which is on deficiency symptoms, where we have photos and we also have a key that allows you to determine or maybe guide you towards what might be deficient in your particular plant. So again, with tissue levels, it's really hard to find critical tissue concentrations. Again, there hasn't been that much work done on that. Chloride is one exception to that rule, and I'll show you some data collected from Montana on chloride tissue levels. In one study done on 87 cornfields, it was found that the only positive correlation between tissue test and yield was for copper, but not for boron, iron, manganese, or zinc. Also, tissue levels will change over the course of the day and over the season. So if you do tissue test, I would first strongly encourage you to call the lab that you're going to send those samples to and ask what part of the plant should I sample and when should I sample it, to make sure the data they have for, say, sufficiency levels or deficiency levels matches what you actually collect. And then do keep in mind, once a deficiency has been observed, you've maybe already lost some growth or some yield. So this was the one I was telling you about where we actually do have, I would say, a very good chloride tissue critical level for the Great Plains states. So what I'm showing here is the whole plant chloride concentration. This is for wheat, ranging from 0 up to about 1.2% on the horizontal axis, and what's called relative yield on the vertical axis. So what relative yield is when no chloride is added to a plot, and then right next to that plot, a full treatment or a full fertilizer rate of chloride is added, usually more than enough. So what this means is when this value is low, well below 1, it means that you get a pretty nice response to chloride. So if you have, say, a 0.7 relative yield, that means you could get another roughly 30% yield boost by applying chloride. If instead your relative yield is 1, that means you grew no more wheat when you had no chloride added as when you had plenty of chloride added. So that's would be considered a non-responsive soil chloride level. What we're looking for is where this chloride tissue concentration essentially gets close to 1, maybe somewhere around 95% or so. And what these authors of our fertilizer fact sheet determined was that somewhere around 0.4% is where below that point, the levels are low enough that it's probably worth fertilizing. Above that point, almost all the points fall right along that 1 line. So it's probably not worth fertilizing. So this would be a great thing to sample would be wheat plants at the boot stage, have them analyzed for chloride if they're, discolored or you suspect chloride deficiency. And then you'll know if you could apply chloride at that point, or you could apply chloride the next year in locations that were low, say this year. So we're saying the chloride level is probably right around 0.4%. I would also recommend basing your fertilizer decisions on multiple sources. So meaning soil test alone does not always seem super reliable, except maybe for copper it is, as I'll show you. We've had conflicting results, say in Northeast Montana, looking at peas and applying different micronutrients where we don't get the responses that we'd expect based on soil testing. So I would recommend integrating soil testing, field scouting for visual deficiencies, and then tissue testing to confirm your results. And then finally, probably the most descriptive, prescriptive way is to do on-farm strip trials where you apply a micronutrient in a strip, none right next to it, observe, and then also you could use a yield monitor to see if you got any response from those strip trials. Any questions whatsoever? It'd be great to get one, just so I know my internet's working, people are still out there, um, and hopefully somebody has a question on something I've covered so far. What are the costs for strip testing? So that would be, there's no set cost. It would be something probably you'd work with a crop advisor. So someone who has access to, say, micronutrient solutions or micronutrient fertilizer, you would add, say, let's say copper sulfate to a seed blend, and you would apply it in one strip until you ran out, maybe flag where you ran out, and then you'd observe. So really, they could be done for maybe just the cost of that product. Sometimes some fertilizer dealers are like, I think this product will work, and they might even help, offset the cost just to run a trial on your farm. So, and then who does plant tissue analysis. So almost every lab that does soil testing also does plant tissue analysis. On my web page, I have a number of extension publications. One is called Soil Test Interpretation for Agriculture, and on the back page of that is a whole list of regional labs that can test soil and can test tissue as well. If you can't find that, just send me an email. Another question was, do heavy metals hinder or affect micronutrient uptake? They can. So all the nutrients can compete with each other. If you have too much of one, it might affect the other. Not so much because it's toxic. A lot of these heavy metals are quite toxic to humans. Probably a little less toxic to microbes, but it's more that they just compete for the same type of nutrients. So for example, if you had a lot of cadmium, the plant might take up that cadmium and not take up zinc. If you have a lot of arsenic, the plant might take up arsenic and not take up boron. So it would be probably a little less from that toxic perspective, but more just that they're there and the plant can only take up so much of similar nutrients. Can micronutrients be added by feeding livestock on fields? Tramp in organic matter and add manure and urine. So if you bring in, say, hay from somewhere else, and then the animals defecate and urinate on that field, certainly those micronutrients in the urine and in the poop will likely be somewhat more available than they were in the material. If they're just grazing the material that's there, that maybe less so because they're taking up, say, zinc that was there in plant tissue. They're pooping it out. It might not increase the availability dramatically, but it might slightly. And you'll probably see that Catherine added the list of labs. With strip trials, my experience, this is from a crop advisor, and that crop advisor writes is, with strip trials, my experience with low soil test chloride on corn silage, the chloride applied resulted in the corn drying down slower, but no yield increase. So corn drying down slower would not be, I think, necessarily a good thing. You'd want it to dry faster, get it off the field, and no yield increase. So likely there was not a chloride deficiency in that field. One thing that we had quite a bit of in some fields is micronutrients from irrigation water. And so there might have been plenty of irrigation water on that cornfield. So thank you for that tidbit. Okay, so on to sources, timing, and placement of micronutrients. Sometimes you'll see something like a micronutrient guaranteed analysis on a bag, and that's generally the total amount of micronutrient there. But what's more important than the total is how available it is. This is a photo showing iron sulfate versus iron oxide. You can see there's really no mineral, no solid left at the bottom of this cup because all of that iron sulfate has dissolved, whereas the iron oxide still exists as iron oxide mineral. So I would steer away from the oxides and more towards the sulfates, which are more soluble. Dwayne Westfall found that he used the term relative availability coefficient, how available are these micronutrients, and he found that zinc, for example, had to be greater than 50% available to be effective for the crop. And then again, some fertilizers do contain heavy metals in excess of safe levels. So what are the different forms of micronutrients you might consider using? Well, there's these sulfates. They're generally water soluble, and you would apply them most likely to the soil. There's something called chelated forms. So chelated is a chemical that's added to those micronutrients. Some of these chemicals we eat, like in mayonnaise, EDTA. That makes that metal more plant available, and that can be added either to the soil or the foliage. There's some that are mix of oxides and sulfate. The oxides aren't going to be very soluble, but the sulfates will be. And then manure has a kind of, I would call it like a slow release because as it breaks down, it will slowly release micronutrients to the soil. The micronutrient source certainly affects application timing and method. I mean, you can't just separate them. So, for example, the most soluble forms of micronutrients should be applied near the time of peak plant growth. If you get them applied too soon before, they will probably stick too strongly to the soil. For products that have low solubility, you might want to add them earlier so they have time to dissolve or break down. Traditionally, we would say probably broadcasting and incorporating them would be ideal, but with so much no-till, that's just not going to work for a no-till farmer. Some cautions, boron, it's needed in very small amounts, but if you apply too much more than those small amounts, you can actually result in toxicity. So I would discourage the use of boron directly with the seed. Foliar, meaning applied to the leaf, that can be done with chelated products. Borate can be applied at low levels. You do need to be a little bit cautious with some of the sulfate or oxysulfate forms. These are soluble salts. They can result in burn if you apply them at too high of levels. So one thing with foliar application of micronutrients, I would discourage using them just as kind of a guarantee. Like I'm going to add it just to make sure I don't have a micronutrient deficiency. I think that's risky because those micronutrients cost money and can result in problems if you already had plenty of those nutrients in your soil. So a good question was what works for no-till. So either seed applied or I would say or applied foliarly would be the only really two options you have since you can't mix those micronutrients down into the soil. For chloride, which is very soluble, that could be added as broadcast potassium chloride, which has a grade of like 0.060. Most people add it for its potassium, but it has a lot of chloride. So make sure you can identify a deficiency either through soil analysis, tissue sampling, or deficiency symptoms. You can make adjustments during the season by, if you notice and are quite certain of a nutrient deficiency. You can use tissue concentrations, but again, chloride's really the only one I have much confidence in. And again, keep in mind that once you see a deficiency, potential yield may already have been reduced. So that's why scouting is really important. Maybe you identify a problem this year that becomes a bigger problem next year, and you know the area in your field to really focus on. Any questions so far on anything I've covered, maybe even clarification of something I just answered, or maybe a question that I missed before? I do see, I think I did miss one. Why are soil tests not always accurate? So two things going on there. One is that um, different laboratories might use slightly different methods. And so by accurate, I just mean, how representative, how good is that? Different people might mix things differently, might add somewhat different amounts. Um, Different labs sometimes use different reagents, and then there's just high amounts of variability in fields and sometimes high amounts of variability within, say, personnel within laboratories. So a lot of different reasons why they might not be accurate, but I do recommend once you've picked a lab to stick with that lab so that you can look for trends over time. Because I think for the most part, labs are generally pretty consistent within that lab. They just might not agree completely with other labs. Other questions? Okay, on to crop response. This is a table where I'm trying to summarize the relative likelihood of response to a specific micronutrient. And I'm doing that for 5 different crops: wheat, barley, beet, alfalfa, and grass, for 5 micronutrients: boron, copper, iron, manganese, and zinc. So anything in red has a low chance of response, meaning relatively low chance that wheat will respond to boron, iron, or zinc, but a fairly high chance that it'll respond to copper and probably manganese. Alfalfa has a high chance of response to boron and copper and low to manganese and zinc. And so this is just what people have compiled over time. So getting a little closer to home, northeast Saskatchewan, this is on a sandy loam soil that had a soil copper level right at the critical level, so 0.4 parts per million. What the researchers did was they monitored spring wheat grain yield in bushels per acre for control, putting 0.2 of a pound per acre of copper in the seed row, about 0.9 of a pound in the seed row of copper, or applying a small amount foliarly. And what you'll notice is that those seed row applications had no benefit on spring wheat grain yield. I think that's because copper sticks so strongly to the soil, it probably wasn't taken up by the plant. Whereas by applying to the leaf, and leaves have stomates on the bottom of them, and some of that product must have gotten taken up, absorbed through the leaf, and corrected the copper deficiency. And notice these are pretty good yield increases. So somewhere around 5 to maybe even 10, 12 bushels per acre over the control easily would pay for itself. This is work done by our neighbors to the north in our 3 western prairie provinces, looking at the effect of soil copper on relative wheat yield. So again, 100% means that fertilizing with additional copper didn't cause any response. Number of relative wheat yield below that level, below 100%, means there was a response. And down here, there was some amazingly good responses, meaning yield might have increased from 20% relative yield up to 100%, an increase of a factor of 5. So the one interesting thing that you can do as a plant scientist or soil scientist is decide, well, what's a good relative wheat yield? Do you want to pick a critical level where you always get 100% somewhere out here, or are you fine taking a little bit of a yield hit, recognizing that adding copper has some cost? And what my colleague from Canada decided to do was pick a relative yield somewhere around 90%, and that worked out to be a soil copper level somewhere around 0.4 parts per million. So below 0.4 parts per million, he would recommend fertilizing, and above, he would recommend not. In Montana, we actually use 0.5. And I think as a farmer, I don't want to take a 10% yield hit. I'm more comfortable maybe taking only a 5% yield hit before I apply copper. So somewhere around 0.5 ppm and below, I would recommend applying copper. In this study, they found that in 52 different fields that had less than 0.4 parts per million, they had a 94% probability of a yield response and a 62% probability of an economic response. Once they got out into this range here, what they call marginal, they had very low response, meaning a low probability of a yield response and a very low probability of an economic benefit. So in other work in Western Canada, the economic responses that they found were either only with a low amount of foliar copper or a fairly high amount of soil applied or incorporated soil copper, granular copper. Often the chelates don't make economic sense when they're soil applied simply because of the additional cost compared to, say, a copper sulfate. Keep in mind the low soluble sources likely will not correct a deficiency. And they found in this study that if they applied more than about 5 pounds of copper per acre, they actually saw a yield decline. So they ran into either a toxicity or maybe the plant took up copper instead of zinc. Chloride has been found to be mostly a problem on small grains. I haven't seen it in other crops. It doesn't mean it doesn't exist. Um, in one pretty large study in Western Canada and in part of the United States on 210 trials looking at for chloride response in both wheat and barley, they found significant yield response in 48% of those trials. So that suggests to me that there's some wide scale chloride deficiencies out there. And the average response was about 5 bushels per acre. Don't even have to really pencil this out. That would certainly have paid for itself. It wasn't really high rates of chloride. Closer to home in Montana, my colleague Rick Engel found a soil that was quite chloride deficient. It only had zero point 0.6 to zero point 0.7 parts per million in the upper 3 feet, which works out to be about 8 pounds of chloride per acre. He noticed severe, what's called flag leaf spot severity, which is the symptom for low chloride in one soil. It yielded about 2,900 pounds per acre, so about 50 bushel, and it had a very low shoot chloride concentration. When he added 40 pounds of chloride per acre, he essentially eliminated that leaf spot severity. He grew another roughly 700 pounds per acre, or about 11 or 12 bushel, and he increased the shoot chloride concentration by about a factor of 10. So we have seen severe chloride deficiencies in Montana. Those have generally been on sandier soils, and people who don't regularly add potassium chloride end up with chloride deficiencies. Any questions on any of that material that I've covered so far? So again, even though I said it's hard to predict, how much fertilizer you should have or add, or even if you have deficiencies, we have seen some pretty strong responses to copper and have what we think is a good copper soil test and to chloride. And we think we have a good tissue chloride test and maybe a good soil chloride test. So Tim is asking, are micro deficiencies more prone to show up over an entire field or will they be spotty throughout a field? So almost always spotty. And I'd say that's probably true for macronutrients too, but I think even more severe or more dramatic for micronutrients. And so just like that image I showed for copper in a field in Canada, there's a very wide range of copper levels and likely some deficiencies in that field, and most of that field probably was sufficient. So if you mix that whole soil or even mix a whole bunch of tissue, you might not find a problem. You really have to focus on the areas where the plants do not look as good and then start looking harder for a deficiency. Great question, Tim. Other questions? All right, I'll keep watching the chat. So zinc has been making the news more in part because there's a lot of people on the earth that do not get enough zinc in their diet. I am going to field this question while I'm still close to chloride. What is the minimum amount of chloride in pounds per acre in the top 24 inches? So I'm assuming by minimum, maybe before you'd fertilize. somewhere around 20 pounds per acre for small grains. I've used 30. I feel that it's maybe a little more than you need, but I'd say anything less than 20 pounds per acre, you should consider fertilizing small grains. We don't have enough evidence on other crops to know where that level is. So zinc. So foliar zinc before flowering has been shown to increase both grain yield and zinc concentration. Selecting for high yield over time as we've gotten better and better at breeding short plants with big grain and high yield, we've decreased seed zinc concentration. Somewhere on the order of 20% of the world's children, maybe even higher, suffer stunted growth from zinc deficiency. And because of that, 26 countries have a mandatory minimum wheat grain zinc concentration standard, with the average standard being 47 parts per million. When I've looked at zinc concentrations in Montana, I'm seeing numbers more like 25 parts per million. If we were to breed for higher zinc grain or maybe fertilize for higher zinc grain, we could help improve the health of these children worldwide. So, in Montana research done at, I think mainly this was a study in Sydney, what the researchers found was that when they added 1 pound of zinc foliarly per acre at heading, they got about a 5% yield increase, a nice increase in the grain zinc concentration, but not enough to get over that 47 part per million threshold. And they actually had a slight net loss. When instead they added 1 pound per acre at heading and another pound per acre at flowering, they saw a 14% yield increase, a grain zinc concentration increase between 35 and 95%, and a net return of $5 per acre. So they did find this second treatment was really needed to get grain zinc above 40 parts per million. There are price incentives for high grain zinc, or if there were price incentives, maybe that would encourage farmers to grow more nourishing wheat, or maybe our markets eventually will dictate that we need to grow higher zinc wheat. Jumping to a crop I don't cover very much, dry beans. This is a study done some time ago on a field in Sydney, Montana, where they looked at the dry bean yield increase in pounds per acre above the control. And they added 7 different forms of zinc, from a foliar zinc, some zinc sulfate applied to the soil, some zinc with other nutrients, and then EDTA is that chemical name for the chelate that I was talking about. What they found was that in every case, there was a boost from adding zinc, kind of regardless of the form. They did find with the foliar application that whether they added zinc sulfate or zinc that was chelated, the yields were about the same. So you might as well add zinc sulfate. It's a lot cheaper. They also pointed out that these EDTAs are quite expensive. So again, probably the zinc sulfates either applied to the soil or applied foliarly are going to give your best chance of a dry bean boost. Another advantage of foliar zinc is it can decrease cadmium concentrations. So cadmium is a toxin, it's a carcinogen, and many Asian countries have a strict limit on how much cadmium can be in grain. It makes sense. We don't want to be eating too much cadmium. So their level is you can't have more than 0.2 parts per million cadmium. Now, cadmium comes naturally in the soil, so it's going to be in grain, but we can keep those levels lower, it appears, with some zinc additions. So here we have grain cadmium level in parts per million for 3 different treatments: no zinc added with the seed, and zinc added to the leaves at what's called boot. Notice that for both the dryland case and the irrigated case, by adding zinc to the leaves at boot, the zinc levels dropped significantly. And in fact, in both fields, the zinc level was below that maximum cadmium level. So a way that you might be able to market your grain better by decreasing cadmium. So in summary, I'd like to point out that a combination of deficiency symptoms, soil testing, and tissue testing, at least for chloride, may be the best approach. Micronutrient deficiencies are generally the exception, not the rule, and are variable within fields. Cool, wet conditions and also dry conditions can cause deficiencies. Too much micronutrient may hurt the yields more than not enough. And make sure to read your product label and look for available micronutrients and watch for heavy metal contamination. And the most conclusive test is probably your own field strip trials. For additional information, I go to my website. Module 7 is on micronutrients, 9 on deficiency symptoms that also has the key I've talked about, and 11 is on fertilizer placement. And with that, I'd like to thank you, and I want to pick off some of the questions that came up since the last questions. Will diverse cover crops with different root structures and depths increase or decrease micronutrients? That's a great question. I've recently completed an 8-year study on diverse cover crops, and we did not look at micronutrient levels. The main micronutrients, the metal micronutrients, probably are increased, their availability is increased as pH goes down. But I don't have great data to say one way or the other way whether they would increase or decrease micronutrients. I would say compared to fallow, they likely would increase micronutrients because organics in general, adding more organic material will increase, should increase micronutrient availability. Do foliar applications affect the soil or the plants for more than that first harvest? Probably not. So again, such low levels are applied, like when you're putting on 0.2 pounds of copper per acre, a little bit goes into the leaf, a little bit sticks to the surface of the soil that falls off or washes off that leaf. Probably a little bit stays in the residue, but for the most part, it's not going to be down in the roots. The only exception to that might be boron, which is a little more available. Maybe chloride, but chloride typically isn't added as a foliar. So these are all great questions. Other questions? And if you do want to jot down my webpage for this presentation and other soil fertility information, you can find that on my webpage. Tim or Catherine, did I miss any questions?
Not that I see, Glenn.
Okay. Okay, any last minute questions? And then I'm going to stop sharing. Did anyone else lose sound? I feel we've gotten those. Did anyone else lose sound before?